Welcome to the ultimate deep dive into TurboQuant. If you have been tracking the AI space, you know models are evolving from 8K context windows to over 100K, and even up to 1 million tokens. But there is a silent killer lurking inside these massive language models, the key-value cache. During text generation, a transformer stores the key and value representations of every past token. It avoids redundant computation, which is great. But the KV cache grows linearly. At a 128,000 token context, even a modest 8 billion parameter model consumes over 40 gigabytes of VRAM just for the cache. Your GPU runs out of memory, performance plummets as data swaps to CPU RAM, and inference grinds to a halt. The obvious solution is quantization. We want to shrink those 16-bit floating point numbers down to 3 or 4 bits. But large language models suffer from an anomaly called extreme outliers. A few specific feature dimensions have activations that are hundreds of times larger than the rest. If we define our quantization buckets to fit these massive spikes, the remaining 99% of our data gets squashed into a single bucket. We lose all our information. Traditionally, researchers bypass this using groupwise or block quantization. They chop the data into tiny blocks of 32 or 64 elements, and assign a unique 16-bit scaling factor to every single block. While this saves the outliers, it introduces a massive memory overhead. If you want a 3-bit cache, adding 16 bits of metadata every 32 values ruins your compression ratio. Enter TurboQuant, a breakthrough framework from Google Research presented at ICLR 2026. It completely solves this using a zero-overhead, two-stage mathematical pipeline. Stage 1 is called PolarQuant. It relies on a beautiful property of high-dimensional geometry, random orthogonal rotation. Before we quantize, we multiply the entire key and value matrices by a fixed, random orthogonal matrix. Imagine a massive spike of energy on one axis. When you randomly rotate the coordinate system, that single spike's energy is smeared and distributed uniformly across every single dimension. By mixing the coordinates, the extreme outliers vanish. The resulting data is isotropic, it forms a perfectly smooth, predictable Gaussian bell curve. Because we mathematically know the data is now Gaussian, we don't need any per-block scaling factors. We can calculate the mathematically optimal quantization buckets globally, using the Lloyd-Max algorithm, entirely offline. TurboQuant maps this data into polar coordinates, radius and angle, and quantizes the entire cache into just 3 bits per element with zero metadata overhead. But wait. Stage 1 is incredibly efficient, but compression always leaves a residual error. In transformers, attention is calculated via inner dot products. If we ignore the residual error, our dot products become mathematically biased, and the model's accuracy degrades. To fix this, TurboQuant introduces Stage 2, the 1-bit quantized Johnson-Lindenstrauss Transform, or QJL. Instead of throwing the residual error away, we project it onto a random Gaussian matrix, and then we take only the sign of the result, a simple +1 or -1. This costs exactly 1 extra bit per element. When calculating the attention score, we compute the dot product of our 3-bit compressed vectors, and we add the dot product of our 1-bit QJL signs. Through the magic of the Johnson-Lindenstrauss lemma, the sign bits perfectly estimate the angle between the residual errors. This totally eliminates the mathematical bias. The attention scores match the original 16-bit model perfectly. The results are staggering. TurboQuant achieves lossless KV cache compression down to 3 or 4 bits. That is a 4 to 6 times memory reduction, allowing 8 times faster attention throughput, with zero model retraining and zero fine-tuning required. It perfectly aces the needle-in-a-haystack retrieval test at massive context lengths. TurboQuant is an elegant, math-driven triumph that unlocks the next generation of extreme context AI on standard consumer hardware. Thanks for watching.